All right, hi everyone. In this video, I'm going to talk about the particle in a box, the real deal, Atkins 7D. The starting point for this is actually the free particle. So in the particle in a box, we have a one-dimensional particle. It moves in X, and there's no potential, right? V is equal to 0, except there are two important differences. And the first is, at some point, we start to put walls on it, right? We imagine that the potential quickly rises to infinity. The second thing we do is that we shrink the box up, right? So we set walls where the potential goes to infinity, and then we start to confine the particle. And we call the edges of this box 0 and L. And we can go through and define the potential then as follows, right? Infinite outside of the box, 0 inside of the box. At this point, we're ready to go through our steps for quantum problems. We'll write the Schrodinger equation and then solve it. I want to make one point. That's my daughter, which was not the point. The point is, if this were a classical system, what would happen? Well, simply, you would just have a particle that whipped back and forth. It would go one way, it'd hit the wall, bounce back, relatively uninteresting. Let's write the Schrodinger equation and solve this. We need to do it in two steps. The first step is going to be outside the box. And H psi equals E psi. Hamiltonian operator has a kinetic energy term. We have a potential term. It equals E psi. Now, outside the box, this potential goes to infinity. And there's a couple different ways that you can think about this, but the only way for this type of problem to work is for the wave function to go to 0. If the potential goes to infinity and the wave function goes to 0, it becomes a limits problem, and you can mathematically manipulate it and make it work. So the solution to this problem is psi equals 0 outside the box. In other words, the particle must be inside box. So that's pretty straightforward. Inside the box. Again, A psi equals E psi. I'm going to write my kinetic energy term. V psi equals E psi. Inside the box, the potential is 0. So this is going to go away. And I'm going to be left with a different equation. Right? So I'm going to write this in a slightly different form. So I took all of my constants and I moved them over to this right-hand side, and I defined a new constant called K. So this is an identical equation. And I want to suggest to you that this should look familiar. Right? This is the exact same thing as the free particle problem. And because of that, the solutions are the same. So we talked about this in a previous video, but for the free particle, the solutions are e to the ikx plus e to the minus ikx. One corresponding to motion in the positive direction, one in the negative direction. And for reasons which will become clear in a second here, I'm actually going to jump ahead a step and use that Euler's relation. Euler's relation says I can take e to the ikx and write it as a combination of sine and cosine terms. And if I do that, I get an expression which looks like this. So this is an equivalent expression which solves the Schrodinger equation, right? Two independent solutions. If I take the second derivative cosine, I get cosine again. At this point, we need to figure out how to get rid of these coefficients, right? These C1 and C2 coefficients. These are two unknowns with one equation. And the way we do that is with boundary conditions. So what's a boundary condition, you ask? Well, it is a condition or a state of the system in which something about it is known. You've already seen this in one place, at least. One example of that would be normalization. I know that if I have a wave function with a normalization constant, when I integrate it over all space, the total probability has to be equal to 1. That's an example of a boundary condition. In this problem, we know a couple things. We know outside the box, psi is equal to 0. We also know from our wave functions that wave function must be continuous. And that imparts two important criteria. Specifically, at the edges, the wave function must be 0. That will satisfy these two boundary conditions. And mathematically, you write that as follows, right? Psi at x equals 0 is equal to psi at x equals L, which is equal, oh, I almost got it, to 0. Right. I can plug this into this expression, right? So if I write psi at x equals 0, I get C1 cosine x times 0 is 0 plus C2 sine of 0. And this is equal to 0. Remember that the sine of 0 is 0. So this one's going to go away. The cosine of 0 is 1. And this condition requires then that C1 be equal to 0. I plug in the other condition. I get C2 sine KL equals 0. So how can I make this be true, this statement to be true? Well, one answer that students commonly give would be to say that, well, C2 could be 0. And that's true. That would work. But then we get an answer of 0 equals 0, right? It's a null solution, so it doesn't really work. There's another way that we can make this problem or this argument equal to 0. And that is as follows. Right? Here's a sine curve. Right? Remember that it has zeros at 0, pi, 2 pi, 3 pi, 4 pi, et cetera, et cetera, et cetera. What if I required that KL were to be equal to some integer number of pi's, where n is equal to 1, 2, 3, dot, dot, dot. If this were true, then this statement would also be true, right? And so this is another way to set this condition equal to 0. At the end of the day, I can solve this expression for k n pi over L, right? I want to emphasize to you here that n is what's called a quantum number, right? It's a quantum number, a counting number that arises naturally when we solve the Schrodinger equation. So it just shows up naturally from the nature of the Schrodinger equation and the wave nature of particles. Once I have this expression for K, I can plug it into this. This is one equation with one unknown. So the last thing I can do is normalize it. You actually did this specific problem earlier. And if you do that, what you'll see is that psi is equal to 2 over L to the 1/2 sine n pi x on L. That is one solution to the Schrodinger equation, or at least one of the things we get out of it, right? Wave functions. The other thing we get out of it are energies. And so this was our definition of K. I can solve this for energy, h bar squared k squared over 2m. I then take my expression for K and I plug this in, h bar squared over 2m, n squared pi squared L squared. Remember that h bar equals h over 2 pi. So some of these pi terms were canceled. And at the end of the day, what you get out of it is this expression, h squared n squared over 8m L squared. N is equal to 1, 2, 3. So we have just solved the Schrodinger equation for the particle in a box, and we got out of it wave functions and energies. Step 2 done. In step 3, we interpret, and I will do that in the next set of videos.